Dear students, I welcome you for the today's lecture related to the stability analysis of control systems. Till now, we have discussed the first order system, second order systems, their transfer function, then the controllers, block diagram, reduction of the block diagram. Now, controllers are there to control the system. But how to control that controller to give you the desired values or to become a stable system, that is of now concern. Controller itself that cannot give you the stability. You have to make that controller so that you will be able to achieve the stability for the system, because the controller that will have their own constants. That is, when you think of a proportional controller, then a steady state gain that will be there, which is nothing but your Kc. Then if it's a integral time constant, then the tau I value and the tau d value if it is a differential controller. So you have to substitute the values for the proportional controller, proportional gain, the time constant for integral, and the time constant for the derivative systems. So when designing of the control system, that is about the stable behavior of the system. So to obtain the stable behavior, your controller itself should behave properly or in a controlled manner. So to be a stable system, you require to have the properly give the values related to the gain, that is nothing but proportional sensitivity controller Kc, the value for integral time constant, and the value for derivative time constant. So you will require all these values. Kc, that is controller gain, it is nothing but tuning parameter and largely determines the controller aggressiveness. This proportional controller gain, it is talking about a tuning parameter. You are going to tune it that it should work in a proper way, and it determines the controller aggressiveness. However, the integral time that determines the amount of integral action. However, the derivative time that determines the amount of derivative action needed for that system, because every system will have a different behavior. A distillation column will behave differently, even though for a same distillation column, if you are operating with different chemicals or with a different composition, this tuning parameter or this derivative or integral time, that will also change, that may also change. Now we have already studied this graph, how the controller that behaves with respect to the time for a step change. So this is the deviation of the control variable, and on the x-axis it's a time. The proportional controller which gives you the offset, The proportional derivative controller that gives you the sinusoidal plus offset. However, the proportional integral that gives you more oscillations, but the offset that is reduced. And in case of the PID controller, both offset and the oscillations, they are reduced. So you must understand this behavior, you must remember this behavior of a controller, and one has to remember this block diagram for any process which is having the controller, control valve and the measuring element. So this block diagram and this action of a controller, that is very much essential to understand this control system. So we are having our defined notation. C is the output or the control variable, R that is the set point, E the error generated from the set point minus the measured value, P is the pressure which is going from the controller to the control valve. Control valve adjusts its position to the manipulated variable, that is the stem position, and which is going to the process. Now there are certain stable systems and unstable system. For that, one has to understand the bounded input and the bounded output. Now when you talk related to the step change, that is a definite step, a definite magnitude that has been defined in case of our step change values. So if it's a step change, which we can see a definite value of certain magnitude that is defined, this value that is defined in case of a step change. Similarly, in case of a sinusoidal change also, the definite value that has been mentioned, and around it is only it is going to vibrate or oscillate. That is why it is called a bounded input. However, if it's a ramp change, then it is continuously bound to increase. There is no limitation. In step change as well as in sinusoidal change, the input itself is a bounded input. That is, within specified limits it will work only. In ramp change, it's unlimited. It can go at a end up to infinite values. So the stable systems, if the bounded input, which is a function of a time and has a definite value, within fixed bounded produces the bounded output. So what is, for a bounded input, the system should be able to produce the bounded output. Then and only then we call that system as a stable system. For a definite or for a bounded input, we are going to obtain the bounded output, and the unstable systems, if it produces the unbounded or unlimited output. Systems are having the input of bounded input, that is, it is within certain range. Now what will be its corresponding output? If it is within certain boundaries, then the system is stable. If it is beyond these boundaries, the system will become unstable. So if we will plot a graph for a certain bounded input of, say, a sinusoidal behavior that is there, this is our bounded input that is there, and if you will plot a graph in terms of a bounded output, then you will also get a certain graph maybe a stable or maybe a sinusoidal graph. For this bounded, that is it is within a certain limits. This is called stable systems. Now, even for the same input or even for the same bounded input, now my graph, if it is behaving like a unbounded system, that is it is going beyond this limits. For every cycle it is going to change its limits, and so that becomes a unstable system. This is what the bounded unbounded output I am getting. This is the bounded output I have got. So there are two systems, two responses for a single input. Single bounded input, we are having the two responses. One is stable, which is within certain limits, that is called the bounded output, and second, which is the unstable, that means it is the unbounded output you are getting. So that is what the stable systems and the unstable system. Now the selection of these values for the gain or proportional sensitivity controller is important and have the stability of a system. Similarly, if the non-oscillatory processes may exhibit oscillatory behavior within the proportional integral controller because of wrong selection of the values of the gain and the integral time constant. So whatever these time constants and the Kc values, that is the gain values I am going to give, my output or my response will become either the within the boundaries or go beyond the boundaries, that is unbounded or bounded inputs. So that is what a non-oscillatory process may exhibit oscillations if I will select the wrong values of the gain or integral time constant. And that is why this analysis of stability characteristics of control systems is essential to study this stability. An unconstrained linear system is said to be the stable if the output response is bounded for all the bounded inputs. Otherwise, it is. Now look at this general control loop in which a transfer function controller, analog to digital converter, the control valve, the process, and you are getting the ys as the output. The input is y set point and ds is the load variable. The notations have changed in this figure. Till now we have used the C, R, U notations. Now if it is a servo mechanism problem, in this y upon ysp that will be there, and if it's a regular mechanism problem, it will become ys upon ds. So the feedback control system will have the transfer function ys upon ysp, that is ys upon ysp, that is nothing but the product of all transfer functions between the ys and ysp upon the product 1 plus product of all transfer functions in the control loop. Similarly, for a regulator problem, that is the transfer function between the y and ds in this figure, or y and u in our regular figures, that is gd of s, that is only the transfer function that will exist. So gd of s upon 1 plus product of all transfer functions. Now coming after the transfer function, we have to consider the open loop systems or the characteristics equation. Since the set point tracking and disturbance, the rejection have the same denominator for their closed loop transfer function, this indicates that both the set point tracking and disturbance, set point tracking, that is YSP or the R, and the disturbance rejection, that is U, or in this figure that is D, have the same general dynamic behavior because their denominator values are same. So the roots of the denominator determine the dynamic characteristics of a closed loop process. So this roots of the denominator of this transfer function determine the characteristic values. That is what the closed loop process. The characteristics equation is given as 1 plus product of all transfer functions in the control system. That is an open loop transfer function that is called. So the open loop transfer function GOL or is the product of all transfer functions in control system when the feedback loop is disconnected from the comparator. When the feedback loop that is disconnected from this comparator. Now this is our feedback loop. This is the feedback loop. So in this we are disconnecting from here and making it an open loop. So YSP, GCS, GAS, GPS, YS and your GS, that will be there. So all these are your transfer functions, that is the product of all transfer functions in a control system. This is what the open loop transfer function is, the product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. So your characteristic equation of a control system becomes 1 plus open loop transfer function. That is what the denominator is. Denominator of the servo mechanism problem or the regulator mechanism problem. This is called as the characteristic equation of a control system. That is 1 plus open loop transfer function is called the characteristic equation, and open loop transfer function is the product of all transfer functions in the control system when the feedback loop is disconnected from the comparator. So two terminologies are more important, that is your open loop transfer function and the characteristic equation. So characteristic equation is 1 plus open loop transfer function equals to 0, and open loop transfer function is the product of all transfer functions in the control system when feedback loop is disconnected from the comparator. So the feedback control system is stable if and only if all the roots of this characteristic equation are negative or having a negative real part. Otherwise the system is unstable. So if the characteristic equation GP, that is your transfer function of the open loop, then if this is the GP which is equal to 0.2 upon S plus 1, for this I can simplify S plus 0.2 Kc minus 1, and which is a single root S which is equal to minus 1 plus 0.2 Kc. The system is stable is that if Kc is less than 5. So how it is? This case, the feedback control system is stable if and only if all the roots of characteristic equation are negative or have the negative real part. Then and only then the system becomes stable. Now, you can have this imaginary part and the real part. So, the right side of this imaginary part, that is, if the roots are positive, then the system becomes unstable. And if the system is having the roots that is in the negative side of the imaginary axis, then the system is stable. So unstable region and stable region, that depends on the roots of the characteristic equation. That is what the characteristic equation is more concerned. So we have tried to understand the open loop transfer function, then 1 plus transfer open loop transfer function, that gives you the characteristic equation. Once the characteristic equation that is obtained, you are going to calculate the roots of this characteristic equation. If the roots of this characteristic equation lies on the right side, that means the positive roots, then the system is unstable. If the roots lies in the left hand side, that is the negative real part, it becomes the stable system. That is, if the roots of characteristic equation of a control system are in the right half of a complex plane, the control system is unstable and the roots have positive real part. If the roots are having the positive real part, then the system is unstable. If the roots are with a negative real part, then the system is stable. And what will happen if the roots lies on this imaginary axis? The system becomes just unstable. If the roots lie on this imaginary axis, the system becomes just unstable. So looking at this figure, this is what imaginary part, imaginary axis and real part. If the roots lies on the left hand side, that means the roots of the characteristics equation are the negative, then the system is stable. Negative real roots, the system is stable. If the roots are on the positive side, then the system becomes your unstable. If the roots lie on the second and third quadrant, then the system may behave the oscillatory behavior. That is, if it's a complex roots, that is the negative real part, the system becomes your complex, and so it's a sinusoidal behavior you can get instead of having a regular or without oscillations. Now in this case you can observe the unbounded, the output is going in an unbounded, continuously increasing output. In this case the output is there sinusoidal, but it is dampening, it reduces the oscillations. However, in this case the oscillations are becoming more and more, the amplitude of oscillation that is increasing when the roots are on the positive side. Now, to understand this, the Routh Hurwitz stability criteria that is developed, Routh Hurwitz stability criteria that is developed, and there are certain rules to understand the characteristics equation and to find that whether the system is stable or unstable. Only thing that by this Routh test or Routh Hurwitz stability criteria, it talks about the system is stable or unstable, but it cannot tell us about the location of the roots. वो रूट्स रियल एक्सिस पे कहां पे है, ये चीजें मुझे पता नहीं होगी, बट सिस्टम के राइट साइड में है, इमेजिनरी पार्ट के राइट साइड में है, रूट्स आर पॉजिटिव, देन द सिस्टम इज अनस्टेबल. If the roots are on the negative side of the imaginary axis, then the system is stable. That one can definitely correlate by understanding this Routh-Hurwitz criteria. Now, how to develop this Routh-Hurwitz array? First, you have to develop an array, and then one has to so you can see the characteristic equation in this figure, that is a1 s raised to n a2 s raised to n minus 1 a3 s raised to n minus 2 a4 s raised to n minus 3 plus dash 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 up to an plus 1, which is equals to 0. This is nothing but a characteristic equation. This is nothing but our characteristic equation, that is 1 plus product of all transfer functions in the open loop control system. So you will get a equation like this. You can see the equation related to this. If this is the system, control loop system, which is incorporating a controller, and the three first order systems are there, so your transfer function becomes like this. And after simplification of transfer function, you will get, 2s square plus 3s square plus s into bracket 1 plus k c plus 2kc, which is equal to 0. Such characteristic equation you will get after simplification of the transfer function. So this equation, that is written in terms of the coefficients a1, a2, a1, a2, a3, a4, and the s raised to the n, s raised to the n minus 1, which is going to decrease, s raised to n minus 2, s raised to n minus 3, and so on, that is s raised to 0 at last, and a raised to n minus 1, where n is the highest power of the s. N represents the highest power of the s. The coefficients of the odd term. Now, the coefficients of the odd term, that is a1, a3, a5, these are your odd terms, a1, a3, a5, and a7. These are your odd terms. And the even terms, that is your a2, a4, a6, a2, a4, a6, a8, that depends on the power of this n. कितना जाने का है? Now you have to draw the columns and the rows. So the first row that will incorporate all the odd coefficients. First row will incorporate all the odd coefficients, and the second row will incorporate all even coefficients. The coefficients of the odd term are A1, A3, while those of the even term are A2, A4, A6. This coefficient of the odd term are kept in the first row, and while the coefficients of the even term in the second row. Then the elements of the first two rows are obtained from this characteristic equation. That is what the use of this characteristic equation is there. From this characteristic equation, we have obtained the coefficients for the first row and the second row. Right? Now, how to obtain the coefficients for the third row, fourth row? That is to be calculated with certain formula. That is the A1, B1, which is the row 3. That is calculated as A2, A3 minus A1, A4 upon A2. But looking at this figure, so A2 and A3 that is there, A2 and A3 that is there, minus this A1 and A4, minus A1 and A4 divided by this A2, divided by this A2. Similarly, the B2 that will be calculated, which is the row 3 and the column 2 coefficient. This will be calculated by considering A2 into the A5, A2 into the A5 minus A1 into the A6, A1 into the A6 divided by the A2. So this is what we are going to calculate the elements of this third row, that is B1, B2, B3, B4. Similarly, the elements for the fourth row, that is your C1, C2, C3, they will be also calculated by using the row 2 and row 3. So C1 that will be calculated by using B1 and A4 minus A2 B2 divided by the B1, that will give me the value of C1. Similarly, C2 value will be by the multiplication of B1 and A6 minus A2 and B3 divided by the B1. You will get the value of C2 like this. Similarly, you can go for the fourth row, fifth row, sixth row. Now, how many rows you have to go? You have to go to the n plus 1 number of rows. N plus 1 number of rows. This is what our n is. If it's the power 3, s raised to the power 3 is there. So n plus 1 number of rows, that means 3 plus 1, that is the 4 rows I have to put. If it's a power 5, then there will be the 6 rows. And the column that will depend on the coefficients raised to the power also, as well as your coefficients. So this is the way one has to develop the Routh array. The first step is to develop a characteristic equation. Characteristic equation is nothing but 1 plus transfer function of open loop transfer function. Open loop transfer function is nothing but the feedback disconnected from the comparator. That means the product of all transfer function in a control loop. So 1 plus product of all transfer functions in a control loop, that is your characteristic equation. Writing that characteristic equation and putting all the odd coefficients in a row 1, putting all even coefficients in a row 2, calculating the value of B1, B2, C1, C2 by multiplying A2, A3 minus A1, A4 divided by the A2. Similarly, B2 that will be calculated as A2, A5, A1, A6 upon the A2. After calculation of B1, B2, B3, B3 that will be calculated as A2, A7 minus A1, A8 divided by the A2. Once you have calculated all the coefficient, all the elements of the row 3, then we can calculate the elements of the row 4 by the similar pattern. Then there are certain rules. The first rule tells that if all the coefficients of the first column, if all the coefficients of the first column are positive and non-zero, then the system is stable for all the values of k. That is the necessary and sufficient condition for the roots of characteristic equation to have the positive real part is that all the elements of the first column of Routh array to be positive and non-zero, so that it is all the coefficients of the first column are positive and non-zero, then the system will be considered to be the stable. This is the first rule. Then the second rule is that the number of roots with the positive real part corresponds to the number of sign changes in the first column. So whenever there is a change in the sign, we have defined that it should be all positive roots. Then the system is stable. That means mostly the roots will come to be the positive. Now, if there is situation that the roots for this comes to the negative, that means there is a change from positive sign to the negative sign, right? So as many number of times this change is from positive to negative or from negative to positive, so many number of roots lies on the right side of the complex plane. That means whenever the system or the roots coefficients of this column 1 changes sign, then your system changes from positive, from stable to unstable, and as many times this sign change is observed, that many times you will have the positive roots. So suppose if A1 and B1, A1 and B1 will have the positive and C1 is negative. C1 is negative or B1 is negative and this C1 that becomes positive. So I am going to change A1 is positive, A2 is positive, then B1 is negative and C1 is again positive. So there is two times a sign change that has been observed. Once is from A2 to B1 and second is from B1 to C1. So there are two changes that is observed. So there are two roots lies on the positive side. Thus we have two sign changes. Hence there must be two roots in the right half of a complex plane. Two roots are on the right half of a complex plane. The next third rule, that is, there is a pair of purely imaginary roots lying equidistant from the origin. That means from 0 0 of the nth row are 0. For this nth row, if this is the 3, nth row means this is the 3 or 4, whatever the coefficient of n. So you are having the row 1, row 2, row 3, n plus 1 are the number of rows. This is row 1, row 2, but you have to calculate up to the n plus 1th row. So if it is a 3 value, then you are going to calculate the 4 rows. If it is 5 value, then you are calculating up to the 6 rows. So whatever the value of the nth row is there, now say in this case it's a 4. N is value of 4. So fourth, then I am going to calculate the PS square plus Q, that is going to give you the location of the pair can be obtained by solving this characteristic equation. That is, there is a pair of purely imaginary root lying equidistant from the origin elements of the nth row are 0, while none of the elements of the n minus 1th row are 0, then you are going to calculate the PS square plus Q, which is equal to 0. P and Q are the first and the second elements of the n minus 1th row. N minus 1th row. If n रो is the fourth, n minus 1th रो में के जो coefficients रहेंगे they are p and q. n minus 1th रो के coefficients है p and q. p and q are the first and the second element of n minus 1th row. These rules are easy to use. There is a limitation, however. For the Routh test only talks about the stability of a system, but it cannot tells us about the location of the roots. Now what are the limitations? That is what one limitation. Routh, it talks about the stability and cannot be used for control system having the transportation lag parameter. It is used only for the system having the polynomial characteristic equations. And it only talks of the stability. It doesn't give you the actual location of the roots for different values of a gain for proportional sensitivity of a controller. So this is the Routh stability criteria